And so I created an algorithm that takes when penalties occurred and incorporates all the nuances from the NHL's rulebook about how you deal with line brawls or how you deal with a goal scored when there's 4 people in the penalty box for one team. I took all that information and created an algorithm that spits out at every second of the game how much time is left on 5-on-4, 5-on-3, etc. And then lastly, my metric provides a flexible framework which can potentially be an umbrella which can unify together a lot of the work being done in other areas of hockey analytics on puck possession, zone starts, and then ideally incorporating in spatial data and other things as they become available. So this is the metric, and I'm not actually going to get very much into the nitty-gritty of the math. It's in my paper, and I'm happy to talk about it after the talk here, but I just want to kind of give you guys some intuition about how it works. So the first thing I'll say is that when the teams are playing at even strength, 5-on-5, the metric simplifies down quite a bit. And it simplifies to this. And what this is saying that the probability that the home team wins the game at time t is equal to the probability the home team wins the game at time t given the score differential at time t. So the score differential being the home team score minus the away team score. So it's a very simple model when it's 5-on-5. When the home team is on a power play, then there's a little bit more to the metric. So the red that you see in the first line there, that represents the probability that the home team scores a power play goal during that power play. The red in the second line represents the probability the away team scores shorthanded during that power play. And then the red in the third line represents the probability that neither team scores a goal during that power play before they return to even strength. And so this is where we have incorporated in this information about how much time is remaining on the power play. So in some sense, everything that you see in red up there, that represents the probability that a goal is scored by one team or the other during some period of time. And so the framework here allows you to incorporate any statistic you want into this model. All you need is some sort of understanding or some sort of statistical model that shows how that statistic impacts goal scoring rates in the NHL. And so you could imagine you have a model that says when Sidney Crosby or Alex Ovechkin is on the ice, this is the goal scoring rate for their teams compared to some random fourth line player where the goal scoring rate is much lower. If you have a rigorous statistical model, you could fit that directly into my framework here. You could also imagine if you have a model that shows how zone starts impact goal scoring rates, or things like Corsi and Fenwick. And then kind of the holy grail here is using spatial data. If we have, at some point in the future, if we have information about where the puck is at every second in the game, we know that when the puck is on one far end of the rink, there's not much of a chance in the next few seconds that it's going to end up in the other net on the other side. So spatial data could potentially be incorporated into this model as well. So I estimate most of the pieces of this model empirically. And the one I'm going to show you here is how we estimate this probability that the home team wins given the score differential, or the home team or the away team. They're symmetric. And so I use data from every regular season game since the 2004-2005 lockout all the way through the 2012-2013 season. So this gives me a lot of data. I have 9,000 games. And I'll show you in a second, I'll show you the graph of the raw data, but you'll see it's a little bit bumpy. There's a little bit of variation across the game. So I just used a weak Bayesian prior distribution to smooth it out so that the curves look a lot better. So this is the raw data. And so what we're looking at here, so start with the red line on the bottom. The red line there represents the probability that the home team wins the game given that the game is tied at every second during the game. And so right at the very beginning, at 20 minutes in the first period, it's at about 55%. So that represents an empirical estimate of home ice advantage in the NHL. Home teams win about 55% of games, but it decays as the game goes on and it continues to be tied. The blue line just above it is the probability that a team with a 1-goal lead wins the game at any point in the game. The green line is a team with a 2-goal lead, their probability of winning, etc. So you can see there's a little bit of bumpiness. And so I apply this Bayesian smoother, and I get these nice smooth curves. And these become the inputs into my metric for calculating these probabilities. So now I'm going to show you guys, now that I've introduced the metric, I'm going to show you guys exactly how you could use the metric to tell stories about the NHL. If you were, say, a journalist or blogger or a fan, you just wanted to understand the game. So this is a game from back in October between the Flyers and the Stars. And I'll before I get into talking about this game, I'll say this: I picked this game because it's very unusual. Most games, one team gets a lead and they kind of maintain that lead, and so their curve it bumps up close to 100 and then just gradually increases toward 100. I picked this one because it's interesting. It tells an interesting story about the game. So you see right here toward the end of the game that Philadelphia scored a game-tying goal with about 5.5 minutes left. When they scored that goal, Dallas's win probability dropped by 38 percentage points. About 30 seconds later, Dallas retook the lead, and when they retook the lead, their chances of winning increased by 39 percentage points. And then just a couple minutes after that, Philly retied the game, and Dallas's probability dropped by 41 percentage points. So if you were writing about this game and you wanted to encapsulate just how crazy a back and forth these last couple minutes were, you could use the data here to really substantiate that point, and to really encapsulate exactly how exciting a game this was to watch. Another thing I'll point out, at the very end of the game, we have this little drop-off here in Dallas's win probability. So this represents a penalty that Dallas took with just a couple seconds left in regulation. And so if you wanted to quantify exactly how costly a penalty that was, this metric helps you to do that. We can say that their chances of winning dropped by 9 percentage points just by virtue of taking that penalty at the end of regulation. So here's another application, and I explain this metric in the paper, but what this is a playoff series win probability based on the individual game probabilities. So what we're looking at is last year's Western Conference Finals between LA and Chicago. And so this is at every second of this 7-game series, the probability that LA won the series. So a few things we can say. So in Game 2, LA was down 1-0, and they were losing Game 2. And at that point in the series, they only had a 14% chance of moving on to the Stanley Cup Finals. Their fortunes changed. They won a couple games in a row, and by Game 5, they had a 3-1 lead. They had a lead in Game 5, and at that point, they had a 95% chance of moving on to the next round. But they lost Games 5 and 6, and by Game 7, with a few minutes left in the game, they were losing, and they only had a 12% chance of moving on to the finals. Of course, you'll remember they tied the game in regulation, won it in overtime. It was really exciting. But if you were writing about this series as a whole, this could give you an idea of just how back and forth these momentum swings were throughout this whole series. So if you're interested in looking at other games, I have a couple apps on my website at winprobs.rinkstats.com. And so you can check out any NHL game that's happened since the 2005-2006 season, and you can pull up the graph there of the win probabilities. I also have a separate app for doing playoff series win probabilities. And you might, if you're familiar with the new analytics blog War on Ice, you might also recognize some of these graphs from there. I've partnered up with them, and so you can find my graphs on their game pages as well. So for the last half of the talk, I'm going to show how we can take this win probability metric and turn it into a statistic that I call added goal value. And so the idea behind added goal value is that not all goals are created equal. And what I mean by this is that when the game is 5-0 and a player scores a 6th goal to go up 6-0, that goal is less valuable to his team than if he had scored that goal as an overtime winning goal. So traditional statistics like total goals or goal scoring rates or goals per 60 minutes masks this fact that not all goals are created equally by just treating all goals as the same. And so the innovation of added goal value is that I'm going to use win probabilities to measure just how big of an impact the goal had on the game. And so players with a high level of added goal value can be thought of as, in some sense, as more clutch offensively. So this is the added goal value metric, and again, I'm not actually going to get too much into the statistics, but I want to kind of give you an idea. So imagine we're calculating added goal value for Sidney Crosby. The red line there, delta K, that represents the change in win probability that results from a goal scored by Crosby. And so it's just the probability just after he scored the goal minus the probability just before he scored the goal. Delta J is the same quantity. It's a change in probability from a goal being scored, but it's by goals being scored by all the other players in the NHL. So this kind of provides a reference group to compare Crosby to. And so when we take the sum of all these delta Ks, so we have all the goals that Crosby scores, and we add up the added win probability from all those goals, we get this in red. When we do the same thing for all the other players in the league, and then divide by the number of goals scored by those other players, we just get the average increase in win probability from a goal scored in the NHL. And so empirically, this is about 17%. That the average goal in the NHL boosts the goal scorer's team's chances of winning by about 17%. When we multiply that average by K, the number of goals scored by Crosby, we get how much would you expect the win probability increase to be if every single one of Crosby's goals was just average. And so if we subtract the blue part here from the red part, we get how much above or below the expected increase in win probability was Crosby's contribution to his team. So I'm going to show you the results here. So on the x-axis, we have goals per game, and this is just the traditional statistic, number of goals divided by number of games. On the y-axis, we have this added goal value metric, and the 0 line there represents a player who's, on average, he contributes about 17 percentage points to his team's chances of winning with his goals. So when we're above the 0 line, we have players who have a high AGV. These are more clutch players. And below the 0 line, we have players that are less clutch. Their goals tend to come, maybe they tend to score their goals as the 6th goal in a 5-0 game instead of an overtime winner. So I'll push those labels to the side just so you can keep them there as a frame of reference. And so this is the scatter plot of every NHL forward since the 2005-2006 season. So I'll point out some of the players who are in here. So up at the top here, we have Pavel Datsyuk, Daniel Briere, Kyle Okposo, Louis Eriksson. These are players who, they're not the most elite in terms of goal scoring, but they do tend to score more than the average player. But not only that, when they score goals, they tend to come in bigger moments in the game. They come in more clutch moments. Right next to them, we have Sakko and Mikko Koivu. I don't have any explanation for why these two brothers are so high on this clutchness measure, except that there's something weird going on in their genes and they were raised really well or something. I'm not sure. Over on the far side of the graph here, we have Alex Ovechkin, Ilya Kovalchuk, Marian Gaborik. These are three players who score a ton of goals, and their goals tend to come in high-impact moments. So these are the players, these are the elite of the elite based on added goal value. Just under them, we have Steven Stamkos, Sidney Crosby, and Jarome Iginla. These are three players that also score a lot of goals, but they're a lot closer to this 0 line. So on average, their probability that they're adding to their team is about 17 percentage points. So something that I should really emphasize here is that this metric is not telling you that you would rather have Mikko Koivu on your team than Sidney Crosby. Because Crosby scores a ton of goals, and every time he scores, he's adding 17 percentage points to his team's chances of winning. Koivu's maybe adding a little bit more, but he doesn't score as often. So this metric is most useful for comparing players who have a very similar goal scoring rate. So it is more legitimate to compare, say, Crosby to Gaborik. Of course, Sidney Crosby has a million other skills that you would rather have on your team. But if all we're looking for is goal scoring and the moments that those goals come in, I would say you would rather have Gaborik. Obviously, a lot of other reasons you'd rather have Crosby, but just on this metric says you'd rather have Gaborik. So you could imagine if you are looking at players who score about 20 to 25 goals per season, then you could compare them right in this row, in this column here. So Kyle Okposo, Brian Little, Curtis Glencross. These three players, they score about the same rate of goals, but they score their goals in very different moments. So Okposo's goals tend to come in the high leverage, high impact moments, whereas Glencross tends to get his goals in lower impact moments. And Little is right on the 0 line there, so he's very average. So let's go back then to where we started. We have these two players. We're trying to evaluate between them which one do we want to add to our roster. Let's see what added goal values can get us. So this is player A's added goal value for the last 5 seasons. In 4 of the last 5 seasons, player A has been below the 0 line on added goal value, so he's been below the league average. Compare that to player B, who in 4 of the last 5 seasons is above the league average. And so something I should point out here is that this metric has a pretty good correlation between years. So if you have a player's added goal value in year 1, the correlation between that and year 2 is pretty strong. It's actually right in the same ballpark as the correlation with Fenwick and Corsi statistics. And so there's good predictive power of this metric across seasons. So who should we acquire? Player B, his added goal value this season is a plus 40 compared to player A's that's a minus 42. And across their careers, player B is a plus 198, player A is a minus 88. So I would say based on this, because they score goals at a similar rate, player B's added goal value and his goals are coming in bigger moments. He's more clutch, and that's the player you want on your team. So who are these players? I don't know if any of you guys have a guess, but player A is Nazem Kadri of the Toronto Maple Leafs, and player B is Matt Duchene of the Colorado Avalanche. So I look forward to hearing your questions, and I also look forward to any suggestions you have about where I can go with this research, but I have a few ideas that I'm going to outline real quickly here. So first, I'd like to enrich the win probability metric by adding more statistics into it, as I explained earlier. And especially as, hopefully, if the NHL is going to make more types of data available, incorporating those into the metric as well. I'd also like to look at creating a metric that evaluates the probability of winning the Stanley Cup at every point during the playoffs. So instead of just an individual game or an individual playoff series, saying how big of an impact did this goal in round 1 have on their team's chances of winning the cup. Similarly, I'd like to create something that does the same but in the regular season and tells us how big of an impact a goal has on the chances of the team qualifying for the playoffs. I'd also like to look at adapting added goal value to the shootout to help evaluate between players and decide which players you maybe want out there in particular moments. I want to look into adding assists into the added goal value metric. Right now it's just goals, but ideally I could have all types of points that go into it. And then lastly, I want to make an app similar to the win probabilities ones that I have, but an app that allows you to compare between players their added goal value so that you can actually look at these decision-making processes. So that's all I have. I look forward to your questions. If you don't have a chance to ask them, I'll be around all weekend, and I'd love to talk to any of you. You can check out my blog there, Rink Stats, and my website is stephenpettigrew.com. You can find my email on there. And also follow me on Twitter. I do a lot of hockey work, but I also write about college football and the NFL and a bunch of other sports as well. So check it out. So thank you guys, appreciate it. So we're gonna have a mic that goes around.
Thanks, Stephen. So we're gonna do a Q&A. We have one question from our review judge first, and then we'll open it up to the audience.
Okay, this question comes from the blinded paper reviewers. It's actually a two-part question.
Okay.
They start off by saying thank you for moving the metrics in hockey forward. It's a field that's not as well developed as the other sports. So thank you for that. That's pretty groundbreaking work you're doing. The first part of the question is you're using essentially a Bayesian updating probability model, and we were wondering what the influence of momentum in a game has on that metric. For context, you know, the Bayesian method looks at a discrete time averaged over a lot of games, which is a great thing to do. But is there an influence of momentum?
Yeah, so the question is about momentum and how that plays into the metric. So the Bayesian updating that's going on, it's nothing more than just smoothing out these rough curves. So if I go back to, I won't try and go back, but the graphs are very jagged. And so the idea is that I didn't want there to be a situation where you have a probability of winning at this time, and then the very next second your probability goes down, even though you still have the same chance of winning. So I just used a simple Bayesian model to smooth those out so that if you have a lead, you're always increasing toward 100%. And so the updating that's going on, it isn't based on momentum in any sense, but it's based on all the empirical data from 9,000 different games. And so what those graphs represent is, you know, at 10 minutes into the second period, if you have a 1-goal lead, in games where that's the situation, I don't remember the exact number, but I'd say probably about 65% of teams win those games. So that's what's going on. And the Bayesian aspect of it isn't so much an updating, it's just making sure that those curves are always increasing toward 100% so that so that it sort of fits the logical eye test.
Awesome, thank you. Are there any other questions?
Stephen, thank you. Quick question. A lot of the players that you have doing well are on fairly average teams. And a lot of the players who don't do particularly well are either on very, very good or very, very bad teams.
Yeah.
Do you have any thoughts on that?
That was something that I thought a lot about after I created the metric. And so the idea might be that if you're on a good team, you tend to have, it's actually a little bit difficult to figure out what direction this bias might go in, because if you're on a good team, you might be tending to blow out teams more often, and so the goals you score might not have a big impact. I've actually looked, though, so I have a graph here. So I just looked. This was every team in the NHL. I calculated the added goal value for all the players on their team, and then just took the team average. And so that's on the y-axis. And when you compare that to the number of points in the standings as of a couple weeks ago, you get that there doesn't seem to be much of a relationship there. It's certainly not statistically significant. So I don't think that there's much of a concern of certain teams having players that there's like a team effect going on here. I think it's just certain players are better than other players along this metric.
Awesome, and we have time for one more question. Okay, right here.
The way your model takes into power plays and stuff, does it consider a goalie pulled situation just 5-on-5, or how does pulling the goalie increase or decrease your odds of winning the game?
So pulling the goalie, if you think about this, so pulling the goalie is sort of I almost consider it a power play in that it's a 6-on-5, and so it's handled in a similar situation. It's kind of a challenge. I only deal with this at the end of games because it's really hard to tease out of the play-by-play data. If there's a penalty and if there's a delayed penalty and the goalie gets pulled, it's possible to pull it out, but there's a little bit of weirdness with the data, and so I don't deal with those situations. But at the end of the game, it's there. Yes.
Awesome. Please join me in thanking Stephen for his presentation.